this video, we will be discussing about maximum number of fish in a grid. You are given a zero index 2D matrix grid of size m cross n, where r, c represents a land cell if it is 0, or a water cell containing these many fishes if it is greater than 0. A fisher can start at any water cell and can do the following operation any number of times. Catch all the fish at that particular cell or move to any adjacent water cell. Return the maximum number of fish the fisher can catch if he chooses his starting cell optimally, or 0 if no water cell exists. So what they are saying is that in the input we are given a m cross n grid, which is this, and in this wherever we have a 0, this denotes that this is a land cell, right? Basically this is a land. And wherever we have a non-zero value, basically a value greater than 0, which is these cells, so this denotes that it is a water cell, right? And the numbers over here denote the number of fishes that are present in that particular cell. For example, here we have 2 fishes, here we have 1 fishes, and so on. Now there is a fisher who wants to collect as many fishes as possible from this grid, right? Now the constraints over here is that if he starts from a cell, firstly that should be a water cell, right? There should be some fishes in that, and he can collect all of these fishes, right? Now from this particular cell, either he can go to the top cell, or to the left cell, or to the right cell, or to the bottom cell. Basically all the 4 neighboring cells, if any of them is a water cell, right? So for example, if he is at this particular cell, then he can collect these 2 fishes, and then either he can go to the left, but on the left it is a land cell. On the top we do not have any cell. On the bottom we again have a land cell, but on the right we have a water cell which contains 1 fish. So he can collect this as well, right? So total he has collected is 3 fishes, right? Then from here, he can either go to this particular cell, but this is a land cell. Towards the bottom, again a land cell. Towards the top, we do not have any cell. And towards the left, this two we have already visited, right? So then that means from this particular cell, he cannot go anywhere, and he can only collect 3 fishes from here, right? So now he wants to collect as many fishes as possible, right? So basically, we need to identify the maximum number of fishes that he can collect, right? So if you will see over here, as I said, when we were at this particular cell, this 2 was already visited. So we didn't visit it again because he has already catched all the fishes which were present in this particular cell, right? So we will also have to keep in mind that we do not visit a cell more than once, right? So now when we check these 2 cells, so what all cells we had visited? This one, this one, this one, this one, and these 2, right? So now we can check for this particular cell. So here he can collect 4 fishes, right? And then the top and the right cells are already visited. On the left we don't have anything, but on the bottom we have a water cell. So he can catch this 1 fish as well. So total fishes became 5. And then from here, top cell already visited, left we don't have anything, and right and bottom cells are land cells, right? So then that means from here he can only collect 5 fishes, right? From here he collected 3 fishes, from here he had collected 5 fishes, right? So now what all cells are already visited? These all are already visited, right? Then this is a land cell, so we can skip this. This is a water cell, so he can collect 3 fishes, and then from here he can collect these 4 fishes as well, and then these will be marked as visited. These are all land cells, so this will be total 7. And then here he can collect these 3 fishes and these 2 fishes, so it will be 5, right? So from here he got 3, from here he got 5, from here also he got 5, and from here we got 7, right? So the maximum out of these is 7. So the answer in this particular case is going to be 7. This is what we need to return, right? So now from here, you would have got an idea already, right? What we are doing is that whenever we are encountering a water cell which is being visited for the first time, we are taking this into account. Basically, we are counting it in our sum, and then we are checking its adjacent cells. If any of the adjacent cell is a water cell, we are considering that, and then we are checking its adjacent cells, right? So that gives us an idea of BFS or DFS, right? So actually BFS and DFS algorithms are a must for solving graph problems, because in most of the graph problems we are applying these 2 algorithms only in some or the other form, and here also we will be applying these algorithms to solve this problem. So see, simply what we can do is that we can start from the starting. Basically we are checking for all the cells. If any of the cell is a water cell and it is not yet visited, right, then what we can do is that from this particular cell we can either apply a BFS or we can apply a DFS, right? Whatever you will apply, you will be able to take into account both of these cells, and these will be marked as visited because of them, right? And then your loop will check for other cells, and as soon as it encounters another water cell which is being visited for the first time, it will apply BFS or DFS for this particular cell, right? So basically your DFS or BFS will be applied for these cells, then for these cells, then for these, and then for these, right? And from all of these you will get a sum. Basically you will get the number of fishes out of these four regions, we can say, right? So what you need to do, you just need to take the max of all of these, right? So simply what you can do is that you can run a for loop of I starting from 0 going till m, and then you can run a for loop of j starting from 0 going till n, and then inside that you can check that if in the grid the value of I comma j is greater than 0, then that means it is a water cell and it is not visited. So you will have to take a visited vector as well to mark the cells as visited. So if it is not visited yet, then what you will do? You will take this into account, right? In the number of fishes, you will add whatever is the value present over here. So basically, instead of just adding over here, what we can do is that we can call a DFS function over here for I comma j, or a BFS function for I comma j, right? So basically this DFS or BFS function will give you the count of fishes for a particular region. So you can take some variable, let's suppose answer. In that you can take the maximum of answer comma your DFS of I comma j, or whatever it is, BFS of I comma j, right? And in DFS or BFS, we will apply normal DFS BFS algorithm, right? So this is what we need to do. So time complexity wise, if we will see, we are running a for loop of m cross n times for each of the cells, right? So basically the time complexity will also be m cross n only, and your BFS or DFS will also be of the same time. Why? Because each of the cell is being visited only once, right? So the overall time complexity will be order of m cross n, and since we will be taking a visited vector, a 2D visited vector, so the space complexity will also be order of m cross n. And also, if you are applying a DFS, then in that your recursion call stack will also take this much space. Because if let us suppose that the entire grid has all the water cells, there are no land cells, then all of these cells will be visited by your DFS, right? So in the worst case, the space taken by the recursive call stack will also be m cross n, right? The space that is being utilized by the 2D vector for marking the cells as visited, that can also be optimized. So that we will understand while we are coding. So now let's look at the code. So here, first of all, let's take the size of the grid. So m will be grid dot size and n will be equals to grid of 0 dot size. And then we can create an answer which will be equals to 0 initially. And then for applying DFS, we need a visited Boolean 2D vector, right? So we will create a vector of vector bool, right? Its name we can keep as visited, and what will be its size m cross n. So m comma vector bool and then n comma false. Initially we will keep all of them as false. Then we will run a for loop of I starting from 0 going till m and I plus plus, and then inside this we will run a for loop of j starting from 0 going till n and then I plus plus, right? Now inside this we will call our DFS function for I comma j, but there are some conditions that if in the grid at I comma j, if this value is greater than 0, meaning it is a water cell and it is not yet visited, so not of visited I comma j. So if these conditions are true, only then we will call our DFS function, right? And that DFS function will return us the count of fishes that can be collected starting from this particular cell, right? So in the answer, we will take the max of answer comma whatever that function returns. So we'll call the DFS function. In that, we will pass the grid and the visited vector, and then we will have to pass I and j, right? So this is what we need to do. And at the end over here, we can return this answer, right? So let's now create the DFS function over here. So this will return us the count of fishes. So int DFS, right? So firstly, it is receiving the grid, then it is receiving the visited vector, then it is receiving the row, and then the column, the current row and the current column, right? So now since here we are applying DFS, and in DFS we will be applying recursion, so there should be some base case. What will be the base cases over here? That if we go out of bounds of grid, right? So basically if row becomes less than 0, or row becomes equals to grid dot size, right? Or column becomes less than 0, or column becomes equals to grid of 0 dot size, right? So these are all out of bound things, right? Then another thing is that if in the grid at this particular cell, if the value is 0, that means it is a land cell. In that particular case also we want to stop. Or the next condition is that if it is visited, if this particular cell is already visited, then also we need to skip it, right? So actually here this should close here and we should remove from here, right? So these will be our base conditions. So if any of these conditions are true, in that case we will return. And what are we going to return? 0, right? And then if none of these conditions are true, then that means it is a water cell which is within the bounds of the grid and it is being visited for the first time, right? So firstly, we can take a variable sum. Basically, this will keep the count of fishes that the fisher can catch starting from this particular cell, right? So here we will initialize it with the value of row comma column. Basically, at the current cell, whatever are the number of fishes present in that we will store in this variable, and then we can mark it as visited, right? So in the visited vector at row comma column, we will mark it as true, right? Now once we have done this, now we want to check all the 4 adjacent cells of this particular cell, right? So for that, let's create a 2D vector for our directions. So this will be directions equals to, first one we can keep as 1 comma 0, then minus 1 comma 0, then 0 comma 1, and then 0 comma minus 1, right? And then we will run a for loop that for auto direction in directions, right? So now our new row will be row plus direction of 0, and the new column will be equals to column plus direction of 1. Right? So once we have done this, we can directly call DFS. Why? Because if this new row and new column is out of bounds, then that condition we have already put over here, right? And if it is 0 or it is already visited, so all of the conditions are present over here. So here we can directly call our DFS function, and that is going to return us the number of fishes, right? So that we will add it in our sum. So sum plus equals to DFS. In this, we are going to pass the grid, the visited vector, the new row, and the new column, right? And at the end over here, we can return this sum. So this is what we need to do, right? So let's try to run this now. So this should actually not be equals to 0. Since it is Boolean, we just need to check that if this is already visited, then we need to return, right? So let's run this again. So right now the test cases are accepted. So now if you see over here that the 2D visited vector that we have taken, we can avoid that. How we can avoid that? So if you see, whenever the value is 0, we are returning. And then from here also, when the value is greater than 0, only then we are calling the DFS function, right? So what we can do is that whenever we are visiting a particular cell, then we can make it as 0. Basically, we can make the value of that particular cell as 0. So our function will always skip it, right? So here we can remove this visited vector, and here also we can remove this particular condition. We do not need to pass it over here. Here also we do not need to receive it. Here we do not need to pass it, right? Here this condition is not needed. We can simply check that the value is equals to 0. And here also, instead of doing this, instead of marking in visited as true, what we will do that in the grid, we will make the value of this particular cell as 0, right? This is what we need to do. So let's try to run this again. So the test cases are accepted. Let's try to submit this. So it got accepted. Now let's try to perform BFS instead of DFS. So we can remove this function and we will create a BFS function which will again return us the count of fishes, right? Now this will also receive the grid and it will receive the row and the column, right? For visited, we will use the grid itself, right? Now, since we are applying BFS, we will need a queue in which we need to store the row and column. So we will take a pair of int comma int. We will name it queue. In this queue, we will push this current cell, which is row comma col, right? And then now we want to take the sum. So now we will initialize it with 0, because when we will apply BFS, then whichever cell we are popping out from our queue, that we will add in our sum, right? So right now here we will initialize it with 0, and then we will check that while our queue does not becomes empty, what we will do, we will take the front cell. So for auto r comma c equals to q dot front. So this will give us the front cell, and then we will pop it from our queue, right? So once you have got this, what you will do, you can check that if in the grid at this particular cell the value is greater than 0, meaning it is a water cell and it is not yet visited. Only then what we will do in the sum, we will add its value, grid of r comma c, right? And once you have done this, you will make its value as 0, marking it as visited, right? Now we want to check all the four adjacent cells, right? So again, we will create a vector int directions. This will be equals to 0 comma 1, 0 comma minus 1, 1 comma 0, and then minus 1 comma 0, right? And then for auto direction in directions, inside this, the new row will be r plus direction of 0, and the new column will be c plus direction of 1, right? So now that you have done this, now here we need to check that this new row and new column should be within the bounds of grid, and the value should be greater than 0. Basically, it should be a water cell. So if nr is greater than equals to 0 and nr is less than grid dot size, and nc is greater than equals to 0 and nc is less than grid of 0 dot size, right? So these are the within bounds condition, and then we need to check that in the grid at nr comma nc the value should be greater than 0. So if these conditions are satisfied, then we will push this particular cell into the queue, right? And then at the end here we can return the sum. So this is how we can apply the BFS, and here instead of DFS we will call BFS, and this is what we need to do. So let's run this again. So the test cases are accepted. Let's try to submit this. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.